Imagine standing in North America 65 million years ago. If you looked up at the night sky, you would see a bright, twinkling light that grew larger and brighter over several hours, yet never seemed to move. A massive mountain of rock, measuring between 7 and 50 miles wide, was hurtling toward Earth at 45,000 miles per hour on a direct intercept course. This rock originated in the Oort cloud, a sphere of icy debris at the edge of our solar system. Researchers believe Jupiter's massive gravity caught a huge comet from this outer ring, pulling it inward and shattering it into fragments we see today. That distant gravitational nudge sent those fragments on a collision course with our planet, triggering the most violent 24 hours in Earth's history. Smaller space rocks hit our atmosphere every day. They act like tiny pebbles thrown into a pond, slowing down and burning up from friction. But this rock was the size of a mountain. It hit the air like a boulder dropped into a shallow puddle. At that massive scale, the Earth's atmosphere offered almost no resistance. The asteroid plunged through all 60 miles of the atmosphere in exactly 3 seconds, screaming over Central America without losing a fraction of its velocity. As it approached the shallow waters of the Yucatan Peninsula, the compressed air in front of it heated to thousands of degrees. That superheated air instantly vaporized the sea below, before the rock even touched the surface. This cross-section animation illustrates a planetary cannonball splash. The impact's pressure made solid bedrock behave like liquid, blasting displaced Earth outward into 20-mile-high walls. Then the crater rebounded, pushing Earth upward at 1,000 miles per hour into a mountain taller than Mount Everest. The initial strike released the energy of more than 1 billion atomic bombs in a fraction of a second. But that staggering blast was only the first domino in a lethal chronological chain reaction. The collision hit the Earth so hard that it literally rang the entire planet like a giant bell. The sheer kinetic force instantly excited the surrounding molecules, creating a blast wave of intense pressure expanding outward at over 1,000 miles per hour. Seismic waves ripped through the Earth's crust at 2.5 miles per second. Within 30 minutes, fault-slipping earthquakes were violently rocking every continent on the globe. The ocean's sudden displacement sent skyscraper-sized walls of water crashing into the coasts. Tsunamis measuring up to 1,000 feet tall pushed tens of miles inland, sweeping away everything in their path and carrying enough force to temporarily reverse the flow of major rivers. While shockwaves decimated the coastlines, trillions of tons of debris launched during the impact were now beginning their descent from the upper atmosphere. Remember that initial 20-mile-high splash of Earth? The impact blasted 25 trillion tons of bedrock straight into space. Within an hour, gravity pulled the vast majority of it right back down as small, glowing, glass-like projectiles known as tektites. Trillions of these chunks, ranging from the size of marbles to school buses, re-entered the atmosphere at the exact same time. The combined friction from their descent heated the global atmosphere to the equivalent of an oven set to broil, spontaneously igniting vast forests and covering the planet in wildfires. This extreme heat acted as a brutal biological filter. Any animal too large to hide was incinerated. Survival suddenly required one highly specific trait: the ability to evade thermal radiation. Only creatures that could dive deep underwater or burrow beneath the baking soil made it through the firestorm. Semi-aquatic reptiles like turtles and crocodiles, along with small burrowing early mammals, successfully waited out the worst of the heat. But escaping the immediate thermal blast was a temporary victory. The asteroid strike had critically broken the planet's atmospheric chemistry. The surviving dinosaurs suffered a final stroke of terrible geographic luck. The Yucatan impact zone was densely packed with subterranean oil and sulfur. The strike instantly vaporized 100 billion tons of toxic sulfur into the upper atmosphere. These chemical vapors quickly condensed into dark storm clouds, returning to the surface as torrents of acid rain and heavy toxic snow. This sudden deluge rapidly acidified the oceans, devastating marine ecosystems. The sulfur was quickly followed by an even darker problem. The impact explosively ejected the equivalent of 150 football stadiums of crude oil into the sky. This oil cooled in the stratosphere, forming a dense, persistent layer of black soot. Acting like a thick coat of paint, that soot completely wrapped the globe, blocking 90% of the sun's light for 2 to 3 years. Without solar radiation, global temperatures plummeted by an average of 50 degrees, starving the surviving plants and turning a lush world into a freezing, barren desert. The giant apex predators that once ruled the planet were buried, eventually becoming the fossils we study today. Meanwhile, those tiny burrowing mammals that successfully hid from the heat slowly evolved, eventually becoming us. But the outer solar system remains exactly as crowded and dangerous as it was 65 million years ago. Fragments of the original comet that destroyed the dinosaurs still cross Earth's orbit on a vast recurring timeline. Today, astronomers actively scan the skies to track potentially hazardous space rocks. They have their eyes firmly on one specific asteroid, named 4660 Nereus, which is scheduled to pass within 745,000 miles of Earth around Valentine's Day in 2060. A minor deviation in orbit is all it takes to put a rock on a direct intercept trajectory. Statistically speaking, another planetary impact is not a matter of if, but when. Preparing a planetary defense is an absolute necessity for our survival. The dinosaurs didn't have a space program, we do. Through advanced physics and massive global coordination, humanity has developed the proactive capabilities to ensure we aren't caught helplessly looking up at a growing point of light. To test these capabilities, NASA launched the Double Asteroid Redirection Test, or DART. The strategy was to autonomously navigate a spacecraft millions of miles through a vacuum and intentionally crash it into an asteroid to alter its speed and trajectory. Their target was this specific asteroid moonlet, Dimorphos. By smashing a probe directly into its surface, scientists successfully proved that a targeted kinetic impact can in fact change a celestial body's course. Deflecting a mountain-sized rock traveling at 45,000 miles per hour will require significantly more force than a single small probe, but the DART mission effectively proved the foundational physics of planetary defense. Deciphering the apocalyptic timeline of the dinosaurs has provided the exact roadmap we need to build a permanent defense system, ensuring our own story continues where theirs ended.